You know, I've always wondered about this. Just how fast do we actually think? It feels instant, right? But behind every single reaction, there's this incredibly complex chain of events firing off at unbelievable speeds. Today, we're going to try and put a clock on that process.
So, let's just start with the big question. How fast is a thought? I mean, can you even measure something that abstract? And the answer is, well, yes and no. We can't put a stopwatch on a single idea, but what we can do is measure the time it takes for our brains to process information and then create a response.
All right, picture this. We've all been there. Your phone slips. That split-second, heart-in-your-throat panic where you try to catch it. In that flash, your eyes see it, your brain registers danger, decides what to do, and fires a command to your hand. We're going to take a journey through that flash of time, from the outside in to clock every single step.
So to figure this out, we're going to start on the outside. We'll look at the stuff we can actually see and measure, just like the early scientists did. This is all about timing our reactions to the world around us.
And this whole field has, honestly, a super cool name, mental chronometry. It's basically the science of clocking the mind. The big idea here is that if you can time a task from start to finish, you can learn a whole lot about all the invisible steps that happen in between. But wait, how do you separate the thinking part from just, seeing something and moving your hand? Well, way back in the 19th century, a scientist named Franciscus Donders came up with this really clever method. First, he measured a simple reaction. You see a light, you press a button. That time includes just seeing and acting. Then he adds a twist. See a red light, press the left button. See a green light, press the right one. This time includes seeing, acting, and making a decision. So you just subtract the simple time from the choice time. And boom, that little bit of leftover time, that's your decision time. It's so smart, right? And this is the perfect way to see it. The only real difference between these two setups is that little bit of extra brain power you need to make a choice. And that extra time it takes, well, that's like a measurable shadow of your thought process. But, that's all on the surface. Let's start peeling back the layers and go inside the brain.
Okay, so before you can react to anything, your brain has to, see it first. So the next logical question is, how long does it take for that signal to get from your eyeballs to the part of your brain that processes vision?
To figure that out, scientists use something called a visual evoked potential, or VEP. It sounds complicated, but the idea is pretty simple. They put some sensors on your head, right over your visual cortex, and they can literally record the electrical spike the moment your brain goes, yep, saw that. It's like getting a delivery confirmation from your brain, right down to the millisecond.
And when they do this, they get some really interesting data. Check this out. This table shows these different electrical waves that happen in your visual cortex. You see a dip around 78 milliseconds, then a big peak around 104, then another dip. These aren't just random blips. Each one is a different stage of your brain making sense of what it's seeing.
But the one we really care about right now is that big positive spike, the P100. On average, it takes about 104 milliseconds, so just a smidge over a tenth of a second for an image to travel from your eye and get its first round of processing in your brain. So there we have it. We've clocked step 1, the speed of sight. Now, what about the last step, the action? All right, your brain has seen the thing. Now it has to tell your body to do something about it. It's got to send that go signal to your muscles. So how fast does that command travel from your brain, down your spinal cord, and out to your hand? Well, for this, they've got another amazing piece of tech. It's called transcranial magnetic stimulation, or TMS. They use a special magnetic coil to basically give the movement control part of your brain a tiny, harmless little nudge. Then they can measure the electrical signal all the way down in your muscle to see how long that message took to arrive. And what they're really measuring here is something called the central motor conduction time, or CMCT. This is the super specific time it takes for that nerve impulse to zip down the main highway from the brain to the spinal cord. It's like measuring the speed on the information autobahn itself. But here's what's really cool. This speed, it's not the same for everybody. It turns out taller people actually have slightly longer conduction times, which makes sense, right? The signal has further to travel. Your age also plays a part. It's just a great reminder that our own internal wiring is totally unique to us. Okay, so we've looked at reaction time, the speed of sight, the speed of a command. We're talking about tiny fractions of a second. You might be wondering, why does any of this matter? Why get so obsessed with milliseconds? Well, let's zoom out and see why this is so important. Because here's the thing. The speed of these signals is a direct window into the health of your entire nervous system. For doctors, a delay of just a few milliseconds could be the very first clue for something like multiple sclerosis, where the insulation around your nerves gets damaged and slows everything down. It can help them spot problems before a person even has symptoms. And even beyond that, there's a clear link between how fast your brain processes things and your overall cognitive skills. These tiny numbers tell a huge story.
And this quote here from Michael Posner, it just nails it. This idea, which was once revolutionary, that you can measure how the mind works by timing how long it takes to do things, well, that's now a fundamental part of how we understand our own brains.
So that's where we land. Our entire experience of the world, every reaction, every decision, it's all built on these lightning-fast processes timed down to the millisecond. Which really leaves you with one big question, doesn't it? What happens when that timing is just a little bit off? The gap between catching your phone and watching it shatter on the floor is just a handful of milliseconds. What other huge parts of our lives are decided in those same tiny moments?